Hello everyone. Today I'll be presenting my work on sputter-deposited PZT-on-Silicon Electro-Optic Modulator. I'm Suraj Singh, working under the guidance of Professor Shankar Kumar Selraja. I'll start with first introducing the communication circuit. So what are the components that are involved in a communication circuit? The first thing that you of course need is a sender that is denoted by sender A and a receiver that is denoted by receiver B. Sender A transmits the information bits in the form of an electrical signal, and receiver B receives the information bits in electrical signal. The components that I would actually be working on is described or is denoted by the modulator driver. So what does a modulator driver does? It converts the electrical information, the electrical bits that are sent by a sender A into a corresponding optical signal, which is then transmitted via optical network to the receiver B, which is at the receiver point is demodulated into electrical signal, which is received by receiver B. Now, we already have this communication circuitry well established in the electrical domain. So why are we actually bothering working in the optical domain? So the bullet point that defines or gives the upper hand to an optical domain is the bandwidth scaling, power consumption, and the packing density. As you can see in the graph on the right hand side of the slide, that as the clock frequency increases, the electrical clock distribution network tends to dissipate more energy as compared to an optical clock distribution network. Now, taking this motivation into account, we proceed ahead with electro-optic modulator design approach. Now, what does a design approach means? Like, what are the mechanisms that you would actually want to choose to have a efficient electro-optic modulator? Once you choose a mechanism, you would want the material that is best suited to harness that mechanism. Once you choose the material, combined, they give a delta N effective, that is the change in refractive index. Now, to maximize the impact of change in refractive index, you would need an efficient waveguide designing. Combining these two, you get an efficient electro-optic modulator. Now, taking these things account of the mechanism, materials, and waveguide design, we proceed ahead to the work that I'm doing. The first one will be the motivation of my work. Second, introduction to PZT, that is lead zirconium titanate, followed by the deposition methods, wise sputtering, then buffer layer, film optimization and characterization, followed by electro-optic modulator device characterization. Now, motivation for PZT. Silicon, as we all know, is a well-established industry with a proper and mature fabrication technology. So why don't we go with silicon? People have gone with silicon and modulators have been reported on silicon. But then as you go on increasing the bandwidth or the frequency of operation of the electro-optic modulator based on silicon, you reach a roof, which is due to the carrier mobility limitation and the RCL limitation. The other option is 3-phi. 3-phi is, of course, it can actually go beyond the limitation of the silicon, but then it's a dedicated platform which you need for 3-phi electro-optic modulator. It's difficult to integrate the 3-phi materials on top of silicon, of course, because of the lattice mismatches that comes on with the 3-phi material. Now, we have an alternative platform. Lithium niobate, of course, it's a very popular material that is being used in the market too for electro-optic modulation. But then the other two options that comes along with this is BTO and PZT. Now, lithium niobate as such has a very small Pockels coefficient, that is 22 picometers per volt. It's a very popular material, but then the possibility of fabricating devices on lithium niobate is difficult because of its inherent material properties. Now, talking about BTO and PZT, both of them give a very high D33 coefficients, more than 300 picometers per volt. But then PZT takes the upper hand or the cake in case of electro-optic modulation solely because it is a very popular material already being used in the MEMS technology, which can further be extrapolated into an optics domain. Hence, it can be deposited on any substrate, followed by its broad wavelength range of operation, gives a very easy way to fabricate electro-optic devices on PZT, which can easily be integrated onto silicon. Now, once we choose PZT as a material or active material which you want to use to make electro-optic device, we define what exactly is PZT and how PZT functions as active devices. PZT as such is an AbO3 class of material which comes under the family of perovskites, where the edges or the points of endpoints of the cubes are occupied by the lead. The face centered is oxygen, and the center of the cube is alternate between titanium and zirconium. So as you can see from the graph on the right-hand side, the first thing that we need to do or optimize is what stoichiometry that we need of the lead zirconium titanate to get the maximum output in electro-optic device. So as you can see, the epsilon 33 and D33 coefficient at 52:48 ratio of zirconium is to titanium gives the maximum value. Hence, the first thing, the target that we need to achieve before moving on to making an electro-optic device is getting the stoichiometry around 52:48, which corresponds to morphotropic phase boundary. And hence, taking this thing into account, we proceed ahead to what deposition methods that we want to make our device, to fabricate our device. The first thing is the solid process. It's widely used, but then it's a liquid process. And then it's limited by the thickness of the film deposited. Chemical vapor deposition and evaporation, you can get PZT, but then it's difficult to achieve the stoichiometry between lead, zirconium, and titanium, solely because of the vapor pressure difference between the three components, that is lead oxide, zirconium, and titanium. Physical vapor deposition helps in maintaining the stoichiometry, but then pulse laser deposition, a very popular physical vapor deposition method, but then it is limited by the scalability. So we go ahead with the sputtering that gives us the benefit of a physical vapor deposition as well as making it a scalable process. So the first thing that we need in an optic device which requires high quality of the film is the film roughnesses, which should be very less for it to function in an optic device environment. The second is the crack density should be minimum, because both of them influence the Pockels coefficient of the material, as well as in case if you use electrode and there are loss of crack density, it can seep through the electrode and hence totally ruin the optical device as such. The parameters that needs to be tuned to get a very good film on of PZT is pressure, temperature, post-deposition anneal, as well as the buffer layer. In all of these conditions, the buffer layer is the first parameter that needs to be optimized or needs to be taken care of before going ahead with the PZT deposition. So the buffer layer we choose is MgO. Why MgO? Because of the two most important properties. The first thing, it is lattice matched with PZT. Its lattice constant is around 4.2 angstrom, which is very near to PZT, as well as a refractive index of 1.7. So it will not only help in the growth of good quality PZT, but also help in making sure that the optical field interacts with the active medium, that is the PZT in our case. So the MgO is deposited using again sputtering and then post-deposition anneal, and we get an MgO, polycrystalline MgO, and that is what is shown in the XRD image. We move ahead with the fabrication of lead zirconium titanate on MgO, and as we can see, with an optimum window in our case of annealing at around 500 to 700 degrees centigrade, we get a crack-free lead zirconium titanate as well as a surface roughness of approximately less than 2 nanometers. And hence we see that with the proper optimization of the film, we get a good quality of the film on MgO SiO2 buffered silicon. So once we have optimized the film, we proceed ahead with the fabrication of the test devices. The test devices are used to first to see whether the film that we are getting, of course, we know that XRD gives us the stoichiometry that we want, but then does it actually behave like a piezo material that the way we want it to? So for that, we go ahead with the PE loop characterization as well as the CV characterization. So from this, we can see that the PE loop and CV loop give us a very characteristic peak splitting that is observed in the case of a piezo material with a PZT thickness of 520 nanometers. So with this characterization, we know that, yeah, our PZT actually works as an active material. We go ahead and deposit the PZT layer on top of our passive device. In our case, it's a silicon waveguide with a racetrack ring structure. And then this is a diagram or schematic diagram of the structure, cross-section view of the structure that we have made, where we have the waveguide, a buffer layer, and on top of it, we have the PZT. So it has been, the measurement has been done pre-polling and post-polling. Pre-polling is done when the new devices are kept at a very high voltage. And in our case, we kept, when increased the voltage in a step value of 20 and went all the way till 80 voltage, kept it for 1 hour, and then let it cool down for another 1.5 hours. And then post-polling measurements were done. After post-polling, we see that we obtain a blue shift of around 12 picometers per volt. Hence, we see that we have achieved an electro-optic modulation with the PZT film that we have got. So in conclusion, we see that the electro-optic demonstration for the first time on silicon on insulator using a wafer scalable sputtered PZT on MGU. The second part and the plus point of this method is it can be integrated on any substrate. The reason being the buffer layer that we have optimized can be made on any of the substrate with an SiO2 intermediate layer, and hence can be integrated on any substrate that we talk of. The electro-optic coefficient 12 picometers per volt, it can be further improved because the film that we have got is a polycrystalline. If we manage to make it a single crystalline as well as able to make the polarization in plane, we can achieve even higher value of the electro-optic coefficient. And the fourth part, from the point of view of ease in fabrication, it can be made patternable, that you don't need to etch out PZT, rather you can do a lift off and hence make the fabrication process very clean and get even better devices than possible than with etching. Thank you.